Welcome to your new unit on acids and bases. So today, to introduce acids and bases, we're going to talk about the different characteristics of acids and bases, as well as some vocabulary that goes along with acids and bases, and some reactions. So first of all, I'm going to start off by comparing and contrasting the characteristics of acids and bases. So acids turn litmus red, while bases will turn litmus blue. So if we go to look at pH paper, which is the same thing as litmus, then if we put pH paper into an acid, well, it turns red. And if we change that to a base, and we put pH paper into a base, it turns it blue. So acids turn litmus red, bases turn litmus blue. And if we put it into water, then there's not really much of a change there. So next characteristic is that both acids and bases are conductive. So we're going to talk about conductivity. I'm going to start off with water, put the electrodes in, and as you can see, the light bulb doesn't really light. So it means that it is not conductive. But if I change that solution to an acid, well, the light bulb lights up very brightly. So it is conductive. And if I change that to a base, again, it is still conductive. Next characteristic is that acids react with metal to form hydrogen gas, and bases will turn pink in a substance called phenolphthalein. And you'll be working with phenolphthalein later on in the unit in different labs that we do. So to show you guys what happens, here's a picture. In the flask here on the left, that's in an acid or a neutral substance, and you can clearly see that that's no color. There's no color there. Well, when you change that substance to a base and you have phenolphthalein in it, then it turns a nice pink color like you see in the flask on the right. Next characteristic is that acids will taste sour. So most of the time, most foods that taste sour have an acid. If you think of lemons, they have citric acid. If you think of vinegar, it also tastes sour. Vinegar is an acid. Well, bases taste bitter. So acids have a pH that is less than 7, and bases have a pH greater than 7. So to show you that, I'll change this to the pH meter, and we'll start off with water. Water has a pH of 7. And when we change it to an acid, it has a pH of 2. And a weak acid has a pH of 4.5. Both of those are less than 7, so they're both acidic. A base, strong base, has a pH of 12, and a weak base pH of 9.5, but both of those greater than 7. So again, those are both basic. And the acids are used to neutralize bases, and bases are used to neutralize acids. And if you touch an acid, you will feel a stinging sensation, especially if you get it into a cut. And if you touch a base, it's going to feel slippery, like soap. So most soaps and household cleaners are actually bases. Well, acids you find them more in food. So, things to know about acids. The definition of an acid, you have two definitions that you need to know. The first definition is the Arrhenius definition, and that is a substance that releases H+ into solution. And H+ ions are also called protons. We're actually going to erase that. Okay, H plus ions are also called protons. So they release protons into solution. So for example, HCl, when it is put into water, it will form H plus aqueous plus Cl minus aqueous. And because it produced this H plus, that makes it an Arrhenius acid. The other definition of an acid is a Bronsted-Lowry acid, and that is a substance that acts as a proton donor. So again, if I take this HCl and I react it with water, the Bronsted-Lowry acid is the HCl, so it means it's a proton donor. So this H plus, this H, is going to go and attach onto the H2O, and it will actually attach onto the oxygen of the H2O. And so when this proton attaches onto the H2O, we're going to get H3O plus aqueous, and what will be left over here is the Cl minus. Okay, and you do need to notice the charges, and you need to make sure that you write the charges, because if you're not writing charges correctly, it's not going to be correct. Also, so this H3O plus is called the hydronium ion. And you do need to know the name of that. So the hydronium ion is H3O plus. So we also need to know what a conjugate acid is, and that's the acid that is formed from receiving a proton. So when this proton transfers onto the water here, and you form this hydronium ion, the H3O plus, this is your conjugate acid. So in the example, the H3O plus, or the hydronium ion, is the conjugate acid. Now moving on to bases, we're going to talk about the same types of things. So the first definition is an Arrhenius base, and an Arrhenius base is a substance that releases hydroxide ions into solution. So this is the hydroxide ion, and we should know this from the common ions that we memorized, but that's a good reminder for us. And so, for example, NaOH, or sodium hydroxide, will break apart into Na plus OH minus. So when it breaks into that OH minus, then it is, and that releases the hydroxide into solution, making it an Arrhenius base. The other definition is a Bronsted-Lowry base. And a Bronsted-Lowry base is a substance that accepts a proton. So if I have NH3 and H2O, this is going to be my base. The NH3 is going to be my base. So if we look at water like this, and this proton is going to attach itself onto the NH3, what we'll be left with over here is the OH minus of the water plus NH4 plus. And again, we have to make sure that we account for those pluses. And that'll be aqueous. And that'll be aqueous. So we also have something called a conjugate base, and that is a base that is formed as a result of losing a proton. So when we had the OH minus plus the NH4 plus, if we look in our example here, this OH minus formed when the water lost a proton, so that makes this the conjugate base. So in our example, the OH minus is a conjugate base. So if we look at this example problem here, and we're going to identify the acid, the base, the conjugate acid, and the conjugate base. So we have NH3 went to form NH4 plus, and we have HC2H3O2 going to form C2H3O2 minus. So the NH3 formed NH4 plus. That means it gained a proton. So the substance that gains a proton is a base, according to the Bronsted-Lowry definition. So this is a base, and that makes, where did it get that H plus from? Well, it got it from the acetic acid here, the HC2H3O2. So that's going to be our acid. That makes NH4 plus the substance that formed as a result of gaining a proton. So that makes that our conjugate acid. And the substance that formed as a result of losing a proton is the C2H3O2 minus, making that the conjugate base. Neutralization reactions. A neutralization reaction is what happens when an acid and a base react. So, an acid and a base react in a neutralization reaction. And so, the acid will always lose a proton, the base gains a proton. Most of the time, we form a salt and water. And when we form a salt and water, this is really just, it's the same thing as a double replacement reaction. So, for example, if I have BaOH2 plus 2HNO3, well, that's going to be barium hydroxide plus nitric acid and well, that's going to form, like in a double replacement reaction, remember your cations or your anions switch places either way. So what will be left with, so this is our anion here. So the nitrate is going to switch places with the hydroxide, giving us barium nitrate plus hydrogen hydroxide. So barium nitrate is BaNO3 2 plus hydrogen hydroxide, that's going to be HOH, which is the same thing as H2O. And in order to balance this, we need two waters. So that is what happens in a neutralization reaction. Remember, you just treat it as a double replacement reaction and things will be nice and easy. Now there's two different ways of classifying acids. So the first way depends upon the number of protons that we have. So in a monoprotic acid, it's a solution that contains only one acidic hydrogen. So an example of that is HCl. There's the subscript of the hydrogen here is 1. A diprotic acid is a solution that contains 2 acidic hydrogens. So an example of that is H2SO4. Notice that there's 2 hydrogens here, so that makes it diprotic. And if it's not monoprotic or diprotic, then it's polyprotic, and that's a solution that contains 2 or more acidic hydrogens. So an example of that is H3PO4. Because the subscript of the hydrogen is 3, then that means that it's polyprotic because there's more than 2 acidic hydrogens. The next, so these are all classifying, so based upon number of hydrogens. And that's acidic hydrogens. So for example, when we looked at acetic acid before, HC2H3O2, this is actually monoprotic because the only acidic hydrogen is out here. These 3 H's are all part of the acetate ion. So they are not acidic at all. It's just this first hydrogen. The next type of classification system is based upon the number of elements that you have in the acid. So the first one is binary, and it's an acid that's made up of 2 elements. So for example, HCl and HF, so HCl, hydrochloric acid, is made up of hydrogen and chlorine, so it's binary, and hydrofluoric acid is made up of hydrogen and fluorine, so it's also binary. If it's not binary, then it is ternary, so it's an acid that's made up of 3 elements. So for example, our acetic acid is HC2H3O2, well, the elements that make it up are hydrogen, oxygen, and carbon. So that's 3 different elements making it ternary. If we go back to here, H2SO4 is also, it's made of hydrogen, sulfur, and oxygen, so that's also ternary. And H3PO4 is made of hydrogen, phosphorus, and oxygen, so it's also ternary as well. And the last thing that we have to discuss is anhydrides. An anhydride is a substance that either forms an acid or a base when it's placed in water. By itself, an anhydride is not an acid or a base, but when it's placed in water, it reacts with the water and forms an acidic or basic substance. So the first type of anhydride are metal oxides. Metal oxides form a base with water to produce a metal hydroxide. So the product is a metal hydroxide. So, for example, sodium oxide, so that's our metal oxide, it's just a metal combined with oxygen. So sodium oxide plus water. Well, it's going to produce a metal hydroxide. What's the metal? Well, it's sodium, so it's going to be sodium hydroxide. Will be our product. Now the formula for sodium hydroxide, sodium has a +1 charge, hydroxide has a -1 charge, so it's just going to be NaOH. Now if I have magnesium oxide plus water, well, the product of that is going to be the metal hydroxide as well, so the metal here is magnesium, so it'll be magnesium hydroxide. So magnesium is Mg, it has a charge of +2. Hydroxide still has a charge of -1, so we need 2 hydroxides to balance that charge out, so it's going to be Mg parentheses OH2. Then if it's a non-metal oxide will form an acid with water. So let's go ahead and erase that pen. Okay, so a non-metal oxide will form an acid with water. So the way that we do that, these are a little bit more complicated. We know that they form an acid, so non-metal oxide, carbon is a non-metal, combined with oxygen, carbon dioxide, it's a non-metal oxide. So we're going to do something that I call making a water sandwich for this. So we're going to take the CO2 and we're going to split the water straight between the H and the O, the 2 and the O. So we're going to put H2 out front, the CO2 is still in the middle there, and O out in the back. And then we're going to squish these together and combine everything that we can. So the product, we're going to have H2, CO, and we're going to add this oxygen to that oxygen, giving us 3. So our product is H2CO3. So if we have nitrogen dioxide and water, we're still going to make a water sandwich. So we'll have H2, NO2, and O. Then, again, we're just going to combine everything together. So it'll be H2, NO3.